Hi, and welcome to part 2 of the time value of money. We're going to build on what we looked at in part number 1. You should have a pretty comfortable grasp of future value, present value, annuities, and annuities due. Here we're going to expand on that, and we're first going to look at what are called amortized loans. This is a variation on an annuity, because loan payments, of course, would represent an annuity, because typical loan payments are the same amount every month, year, quarter, what have you. An amortized loan, just so you know the definition, is a loan where each payment includes both interest and principal, so principal and interest in each payment, such that at the end of the loan period, however many years the loan might be, the loan is fully paid back at that point. That's a fully amortized loan. What we're going to look at here is solving for payments. I mentioned in the earlier video that the calculator would happily solve for any of the time value of money variables as long as we gave it all of the other ones. So there are 5 key variables in time value of money. As long as you give it 4 of them, it'll solve for the 5th. So this is not going to be too complicated, but we are going to look at payments. And let's look at an example here. If we borrow $5,000 from our parents to buy a used car, we agree to make payments at the end of each year for the next 5 years. If the interest rate's 6%, how much is the payment? So now we're not asking, like before, what is the future value or what's the present value, but rather, how much is the payment? Now, clearly this is an annuity. The payments are going to be an annuity. So we can use the present value of an annuity equation that we had before, and we set the present value equal to the amount we're getting today. And then we enter everything else in. We're going to solve for payment. So here is the payment. There's our answer. But how do we do this in the calculator? Because this is, just kind of tedious to use the equation. So in this case, my n is 5. I'm going to take 5 years to repay them. They're charging me 6% interest, so 6 is my interest per year. Present value, that's what's happening today. Well, today they're handing me $5,000. So that's a positive $5,000 that's going to go into present value. And you might say, wait a minute, I'm paying $5,000 for the car, so that's a negative cash flow. No, for the term of the loan, from the loan's perspective, they're giving you the $5,000 today, and then you're going to pay them back the payments. So the payments are going to actually end up being negative in our solution. The fact that you spent the $5,000 on a car is a separate transaction from the loan itself. So the present value is $5,000. We're solving for payment. Future value, 0. What we're saying there is that at the end of the 5 years, we want the balance to be fully paid back. So the future value is going to be 0. We're making 1 payment per year. So their periods per year is 1. Beginning or end mode. It says right here, end of each year. N is a loan. Loans are always end mode. So we're going to put end mode here. If we go to our calculator, we need to verify that we'll get the same 1186.98 number. If I pull up my Excel calculator, N in this case is 5, interest rate is 6, present value, they're handing me $5,000. I want to solve for payment, beginning or end mode, there it is. If I leave my payment blank here, 1186.98 is the solution, and that verifies what we got with the equation, which is a good sign. So that is simply solving for payment, knowing the present value and future value, interest rate and term, solving for the payment. Calculator makes this quite simple. One thing that's bizarre, though, here, we have a loan that is yearly payments. Now, because this is a deal with our parents, we can set up whatever arrangement we want, but this would be a very strange kind of a loan for a car. A more typical situation is the following. Let's pretend we borrow $20,000 from the bank to buy a used car, a little nicer used car than before. We agree to make payments at the end of each month for the next 4 years. If the interest rate's 9%, how much is my monthly payment? So here is the first time that we're going to have a situation where we have more than 1 period per year. In this case, monthly periods, how many of those are in a year? Well, there are 12 of those in a year. So we're going to set our periods per year setting to 12. Now, over here, using the equation, it's not a big deal. What we have, though, here, our n is the total number of periods. In this case, 48. What we have to make sure in the equation, if you're using the equation, K is always in per period terms. So you can see here we're not using 9%. We're using 0.75% in decimal format, and that's because 9% per year divided by 12 is 0.75%. So we have to use a per period interest rate and a per period N to get the correct answer here of 497.70. Now, if that seems kind of confusing, we'll go to the calculator and it should be a little more straightforward. My N, what is my N? Well, it's 4 years. And in the past, all the calculations we've done, we would put a 4 in there, but not now. And the reason is, look at what this is labeled, N. N is always, always, always the total number of periods. We have monthly periods. How many are there? 48. And you might say, wait a minute, Chris, we put 12 down here, so the calculator should make the adjustment. It does not adjust N. If it did, that would be labeled Y, and you would always put years in there. It's labeled N for a reason. It's the total number of periods. So in this case, 48. And then the next entry, interest per year. And the reason why most calculators do this instead of the K concept from the equation, which is a per period, in this case, K is the interest per month. The reason why we do interest per year is that most of the times in finance, when we kick around interest rates in discussion, if we're hanging out at the bar talking about loan interest rates, when we're talking about 9% versus 7%, we don't want to always have to say annually or per year. That's just a waste of a lot of vocal cord use. So we all just know in the finance world that when we're kicking around interest rates, unless we say something otherwise, the assumption is that's always annual terms. And that's the case here. This 9% is annually, so we're going to just put 9 right here. The reason why we do this in the calculator with the 12 is that it then knows how to adjust for this and turns it into a monthly rate. But the calculator does that behind the scenes. We don't have to worry about it. Present value, they're giving me 20,000, so there's my present value. I'm solving for payment, and I have no future value. Once again, in a loan situation, that means at the end of the 4 years, there should be no balance left. And is it beginning or end mode? Well, loans are always end mode, plus it even states end mode. So I'm going to put it in end mode. So on the calculator, how are we going to do this? Well, very straightforward. We should be pretty practiced at this now. My N is 48. My interest per year is 9. They're giving me 20,000. But my periods per year, and this, as I stop right here, if I were making annual payments, that's how many annual payments I'd have to make over 48 years. Now, that would be a very bizarre situation. I need to change this to 12. And lo and behold, there's my 497.70, which matches what I get from the equation, which is correct. So you can see on the calculator, the periods per year setting, because we're dealing with monthly periods, there are 12 of those in a year. If we were dealing with semi-annual periods, that means 2 per year. Quarterly means 4 per year. Daily means 365 per year. I think you get the drift. So this is our first use of that periods per year, or payment. Some people call it payments per year. Both are true depending on the particular problem you're dealing with. Not always necessarily, but I prefer the more generic term periods per year. But here we're talking about payments, so you could easily call this 12 payments per year. Let's practice this on your own. So this is another loan problem. As before, pause this, do this on your own, and then I will work through it and you can check to see if you got it correct. Okay, now that you're back, if you take out a 30-year fixed rate mortgage of $500,000, what will be the monthly payment if your loan has a 6% annual interest rate? Well, as always, let's just fill these in. My periods per year, this is monthly payments, so my periods per year is 12. Their end mode, as loan payments always are, my N is equal to 360. 30 years, 12 times a year is 360. The annual interest rate is 6%. I'm receiving $500,000 from the bank or mortgage company. I want to know the payment, and at the end of the 30 years, I don't want to owe any more money. I'm just going to state that the future value is equal to 0. Well, on the calculator, here's our solution. My N is 360. Interest per year is 6. They're handing me $500,000. And there it is. My monthly payment, $29.9775. That would be principal and interest on that loan. That's the amount each month I would need to pay, such that at the end of 30 years, I will have paid back the whole $500,000 as long as all the interest that's accruing over that 30-year period. That's my solution. Hopefully you got the correct answer. Next variation on annuities, what's called perpetuities. A perpetuity is an annuity that goes on forever. Think of it as the combination between the words perpetual and annuity. The reason why we talk about this, you might wonder, why are we talking about a perpetuity as a concept? Because nothing goes on forever. Well, in finance, there actually is a financial instrument that behaves like a perpetuity, that pays a fixed dollar amount every year, and there's no ending date to it. So technically or theoretically, it goes on forever. Now, the only concept on a perpetuity we discuss is the present value of a perpetuity. And you might think, well, that's got to be an impossible calculation because there's an infinite number of them. I'm not going to go through the derivation of it at this point, but the good news is the present value of a perpetuity simplifies to this very, very easy equation. It is the payment divided by the discount rate or required rate of return. Now, what is that financial instrument that acts like a perpetuity? It is preferred stock. We're not going to go into a lot of depth on what preferred stock is at this point, but preferred stock pays a fixed dividend in almost all cases. And what we're talking about here is kind of plain vanilla preferred stock. And traditional preferred stock pays a constant dividend, and there's no ending date. So technically, it's a perpetuity. The question here is, if a share of preferred stock pays a constant dividend of $5 a year, what is the present value? Or another way of saying it, what is it worth? What is it worth today? Well, the answer very simply, as you can see here, is $62.50. The $5 divided by the 8% required return. So to interpret this, what this means to us in finance is that if my required rate of return, so if as an investor my required rate of return is 8%, that share of preferred stock is worth to me $62.50. Otherwise, in other words, I would be willing to pay up to $62.50 to invest in that, because if I do pay $62.50, I will receive my required return. Now, to prove that, let's think of it backwards. If I had $62.50 and I put it in a bank that earns 8% per year, how much could I go take out at the end of every year forever and never run out of money? Well, if I put $62.50 in the bank and I earn 8%, how much is going to be in the bank at the end of the year? Well, 8% of $62.50 is $5. There's going to be $67.50 in there at the end of the year. If I take $5 out, it goes back to $62.50. How many years can I do that before I run out of money? It won't ever run out. It'll go on forever. So here's the proof of this concept. If I invest $62.50 and earn 8%, I can withdraw or receive back $5 a year forever. So going back the forward way in the present value of a perpetuity calculation, if instead I know the payment, the $5, and I have a required rate of return of 8%, I can solve for what is that preferred stock share worth to me. I'd be willing to pay $62.50 for it, because at that investment level, the $5 a year will be generating for me the 8% return that I'm demanding. That's perpetuities. We've dealt with a lot so far. future value and present value of lump sums, future value and present value of annuities and annuities due. We've solved for payments on annuities, which we called amortized loans. We looked at perpetuities. Now we're going to deal with another common situation, which is what's called uneven cash flows. Many times we're dealing with a situation where we have neither a lump sum nor annuity payments. We have repeating cash flows, but the cash flows vary. They're uneven. Well, we can't use the annuity solutions that we have before because this is not an annuity. So let's look at how this would play out. And we're actually going to use Excel to do this. The question is, how much would the following cash flows be worth today if I could earn 8% on my deposits? So essentially this is saying use 8% as the discount rate, present value all these cash flows. Well, here's the brute force approach. I'm going to discount back all of these cash flows to today, add them up, there's my answer. This series of cash flows is worth $21,454,380 if my discount rate is 8%. That should be pretty straightforward based on the previous work we've done with present value. But let's look at some more efficient ways to handle this. This, in other terms, we essentially have a situation, a line of cash flows that we can call cash flow 0, because that's at time 0, cash flow 1, 2, 3, and 4. Well, there's a tool in most financial calculators, as well as in Excel, that is designed to handle these uneven cash flows. Now, the most common place we see these uneven cash flows are in what are called capital budgeting decision-making projects, where we're deciding, should we invest in a project, and we're trying to value that project. And one of the techniques that we use is called NPV, or net present value. We're not going to go into what net present value means right now, but we're going to use the net present value tool because it's designed to handle uneven cash flows. We're going to use it simply to get the present value of these uneven cash flows. Now, the present value, of course, is this. Let's look how we would do that using the NPV function. So in Excel, I'm going to go off to the side here. This isn't automatically built in here, but what I'm going to do is I'm going to just show you quickly in Excel how to use the NPV function. If I line these up, if I have cash flow 0 through 4 here, I'll just type them in. 7 million, 2 million, 4 million, and 6 million twice. So this is my list of uneven cash flows. Now the NPV function, if I hit equals NPV and then open parentheses, it's going to prompt me for what it needs. The first variable, it needs the rate, that's the discount rate, comma, value 1, value 2, and so on. So here's where I can list all the different values in here. And in this case, something I need to point out, and if you open up the NPV help feature here, which I'm going to do for you, I'm going to point out a couple things. It calculates the net present value of an investment by using a discount rate and a series of future payments. I need to mention something. Value 1, value 2, etc. NPV investment begins one period before the date of the value 1 cash flow. So what that means is value 1 is 1 year from now. So you can see in the NPV equation, the first thing it's asking for is value 1, not value 0, which is the 7 million. So here, look how I'd build this. And this is improper Excel use. I'd normally reference the discount rate, but I'm just going to type it in, the 0.08, comma, value 1, 2, 3, and 4. That's cash flows 1 through 4. And then I close the function, but you hopefully are thinking, wait a minute, what about the 7 million? I have to manually add the 7 million outside of the NPV function. And lo and behold, there's the 21,454,379.70, which is what we got before. That's simply because of the format of the NPV function in Excel. The values inside the parentheses start with cash flows 1, 2, 3, and 4 at years 1, 2, 3, and 4. The first cash flow in the parentheses is not I repeat, is not cash flow zero. That must be handled externally. So you can see that inside the function we have these four, and then we manually add the present value, the present value cash flow, which is the cash flow at time zero, has to be added in there to get the total present value of what's going on here. Now, those of you who move on and do some capital budgeting work, which might be some classes, not in others, you will see exactly why they do this and how this function can be used in that context. But for us here, if we want the present value of all of these, we include cash flows 1 through 4 in the parentheses. It discounts those back using the rate that I've defined, in this case the 8%, and then I have to manually add in the 7 million in order to get my final answer of 21,454, 380 rounded to the nearest dollar. Now we've solved for present value, future value, payment, but we haven't solved for K or for N. So let's take a look at that. Here's an example. If I have $200 and it grows to $230 over 2 years, what is the annual return on this investment? In other words, what is K? What is the interest per year that I'm earning on this investment? Well, I can use the basic future value, present value equation that we've developed before and solve for K. And you can see that 7.24 is the correct answer. But what if I want to use the calculator? Well, in this case, my N is 2 years, 1 per year. There's my default periods per year. Beginning or end mode is irrelevant because beginning or end mode only concerns the timing of a payment, and there is no payment in this case. So I'll just leave this end mode as the default. Interest per year is what I'm solving for. The present value, what's going on today, I am investing $200. So that has to be negative. And then I'm receiving $230. And this is crucial. If you don't have opposite signs on present value and future value, you will get an error because essentially, let's pretend that I entered in 200 and 230, both positive. What you've told the calculator is that today someone hands you $200, and then in 2 years that person hands you another $230, and then you're asking the calculator what rate of return is that? Well, that's no rate of return. That's just $430 of free money. So we have to describe the problem correctly for the calculator to handle it. And in this case, it's investing 200, so that's a negative, receiving 230, that's a positive, then the calculator can handle it. So in Excel, going back to my calculator here, my N is 2 years. Oops, need to bail out of there. My N is 2 years, 1 period per year. I'm solving for interest per year. Present value is the negative 200. There is no payment. I then receive 230, and there's my 7.24. Everything works like it should. Now, just for fun, let's see how broken this thing can be. If I put 200 in, look at that. I get an error. There's no solution for this particular problem. It cannot solve this. There is no rate of return if you put those signs in incorrectly. So I do the negative 200. There's our 7.24. Now, one specific thing, and this is talked about in the text, so we need to cover it. Solving for K, or rate of return in the bond world. Well, in the bond world, the rate of return is called yield to maturity. Now, I'm not going to spend a lot of time describing all of the elements to bonds, but those of you who need that information, I'm sure we'll take some sort of investments class where you'll go over this in great detail. In short, a bond is a form of a loan that a company uses to fund itself. They will borrow money, and then they will make interest payments called coupon payments back to the investor. In this case, this company is going to pay a semi-annual or twice per year coupon payment of $300. At the end of the bond maturity, which is right here, this is the end of the loan, so this is a 15-year bond, the company will pay a lump sum of $10,000 at the end, and the yield to maturity is what we call the total return on the bond. Now, the total return on the bond includes two things. The total return comes from two places. These coupon payments plus the difference between the price that's paid now and the par value, that's what's paid at the end. Par value is the terminology in the bond world that indicates how much is paid on the last day when it matures. So this bond, 15 years, they're going to pay the investor $300 every 6 months, plus on the last day pay $10,000. At that point, the bond will be finished, extinguished, redeemed is the correct terminology. And the investor, if they pay $9,300, will have gotten money two ways. They will have made $700 by paying $9,300 and getting $10,000, and also got the $300 every 6 months. The yield to maturity captures both of those things. Well, the calculation is actually pretty straightforward. In this particular case, we can describe this to the calculator and have it solve for the yield to maturity. So my N here, my N is the total number of periods. Well, I've got semi-annual coupon payments happening, so I'm going to receive $300 payments twice per year. That's what semi-annual means. They're going to come to me at the end of every 6 months, so this is end mode. In the future, at the end, I'm going to receive $10,000. So there's my future value. Today, I'm going to pay $9,300. And this is going to happen, these payments are going to happen 30 times. My N is 30, 15 years, twice per year. And I want to solve for that rate of return, what that might be. Well, in this case, let's check and see what that is. On my Excel calculator, my N is 30. My periods per year is 2, because these are coming semi-annually. Payments, I'm getting $300. I'm also getting $10,000 at the end, and I'm paying $9,300 today. And you know what? I got the wrong future value. That's $100,000. $10,000. There's my solution. 6.75%. Now, it'd be nice to invest $9,300 and get $100,000, but that's not going to be the case in this one. That was my typo. So 6.75% is the answer. I'm going to make money from the coupon payments and money from only paying $9,300 and getting $10,000 at the end for a total annual compound rate of return of 6.75%, which in the bond world we call the yield to maturity. The total return if I hold the bond to maturity, which is at the end in 15 years. We also have times when we need to solve for N, how long it's going to take for something to happen. Here's a prime example. If you need to accumulate $50,000 to go on vacation, how long will it take to amass that much in an account earning 8.5% if you plan to save $200 per month? So I have a few things going on here. I have monthly periods. I've got a goal. I've got $50,000. That is a future value because that's what I need in the future. I'm going to earn a certain amount, and the question is how long. Anytime you see how long, that's solving for N. So in this case, per month means 12 periods per year. Nothing in here says anything about starting today or the beginning of the period, so we're going to assume here this is end mode. I'm going to put the $200 in at the end of every month. That's the base assumption unless we're told differently. My N in this case, I'm going to solve for N. My interest per year, 8.5%. Present value, 0. I'm starting with nothing, but then I'm putting away $200 every month. That's my investment, thus it's negative. The future value, what I need in the future, $50,000. That's my goal. So the question is, what is my N? How long is this going to take? Sorry, my mouse again is acting crazy. So my n here, I'm solving for n, so I leave that blank. My interest per year, 8.5%. Present value is 0. I'm putting away 200 bucks every month, so my periods per year is 12. And I need $50,000 at the end. There's my solution. 144 periods. How long are my periods? 144 is my n, and that's months, because my periods, I define my periods right here. There's 12 per year, so that's monthly. So it doesn't take 144 years. That would take a very long time, obviously. You probably wouldn't enjoy that vacation very much. But I divide this by 12, and I get 12 years. There is my answer in years, which is typically how you would portray this type of information. 12 years, and I'm heading out on my dream vacation. If all of this, if I put in $200 a month and earn 8.5%, I'll have my 50 grand and I'll head on out. Sounds like a long time for my vacation, but it is my dream vacation, so I guess I only can expect to have one of those per year, or one of those per lifetime. One dream vacation per year, that's a good goal maybe for retirement. Last topic for this section, we need to talk about what happens when a situation or an investing situation is compounded more than once per year. We know how compounding works. We earn interest on the original amount we put in, what we call the principal, plus interest on previously earned interest. Well, let's take a simple example. $500 invested at 9% for 2 years. I'm going to draw the timeline to show you how this is going to work. So, if I put in $500 at the beginning of the year and I earn 9%, what am I going to have at the end of the first year? Well, clearly $545. I'm going to earn 9%. And then I'm going to earn 9% on the $545, and that's how I'm going to get to the $594.05. That's the annual compounding. Essentially what we're saying is that 500 sits in here all year long, and then they credit me the 9% that they're promising me. And then the 545 sits in here all year long, and then they credit me or calculate the interest of 9% on this balance. Now let's compare that instead to the second example, semi-annual compounding, but still at 9% and still for 2 years. Let's put the timeline up. What's going to happen here, I have my 2 years and I put $500 in. The difference is after 6 months, they're going to say, well, we're going to credit you interest now because we calculate the interest semi-annually. But they're not going to give you 9% because that's for the year. They're only going to give you 4.5%, which is $22.50. So in the second, after the end of 6 months, you've got $522.50 in there. Here's where the difference occurs. In the second half of that year, so this next 6 months, you're going to earn the other 4.5%, but not on 500. You're going to earn 4.5% on 522.50. And you're going to end up with more than $545 there. We could easily figure out what that is, but at the end of 2 years, with this effect, look at the difference. You're going to have $596.26 at the end instead of $594.05. Not because you had a higher interest rate or you left it in longer, but simply because the interest was being compounded more frequently. Well, that right there is going to cause you to have more interest calculation, more dollars of interest calculated simply if your compounding frequency increases. So here it goes from once per year to 2 per year, and this is 4 times per year, 12 times per year, 365 times per year. But something you have to notice is it increases, but at a decreasing rate. So there is this effect has a limit. Now that limit is reached at what we call continuous compounding, which is essentially compounding infinite number of times per year. And you might think, well, gee, that, if you go from 365 to infinite, it has to make a big difference. Well, you can't use the traditional calculator because the calculator doesn't have the infinity button on it. We can't put in infinity for periods per year and 2 times infinity for n, which is what we'd have to do. That obviously isn't going to work. But there's a function, the e function, the that's the natural antilog of 1, for those of you who are keeping score at home. E is kind of like pi. It describes a specific logarithmic relationship. It's technically the antilog, but it describes this function looks like this. Okay, and this exactly is how this works. We reach a limit. As the number of compounding periods goes to infinity, the future value has an uppermost limit, and it'll never go above that, and that's what we're solving for right here. So in this case, different calculators will do this a little bit differently. I can, let me load up my calculator real quick. Let me pause here. I'll bring it up. Okay, I've got my calculator here. So to solve this on a calculator, you can do this in Excel as well, but on the calculator it's a little bit easier to see. What I have to do here is I have to get k times n, which is going to be 0.09, the 9%, times 2, my number of years, that's 0.18. Now I need to raise e to that power. On this calculator, you do that. You can see e to the x right above the ln here. So with 0.18 on the screen, I hit second e to the x. That's e raised to the 1.1972, and it goes out beyond that. I'm just showing 4 decimal places. And the last thing that I need to do is multiply by my present value, 500. And you can see, lo and behold, there's my 598.61, which is what's displayed here. And you can see the whopping difference between that and daily. There's a whole penny difference. Well, you might think, well, that's a lot of work for not much difference, but we're only dealing with 2 years. We're only dealing with $500. And there are cases in finance where continuous compounding and continuous discounting is appropriate, in particular in the area of options pricing, which was not an area that we're going to cover here, but you do need to know the concept of continuous compounding, and before that, the effects of increasing compounding frequency. As we increase the compounding frequency, the future value increases, but at a decreasing rate. That is the end of part number 2. If you have any questions, let me know. Practice, practice, practice. That's the key to time value of money problems. So work as many end of chapter problems as you have time for.